So thank you very much. So I have slightly changed the title because I think machine learning would have been a bit misleading, because I'm really only going to get to machine learning at the very end, if at all. But so what I want to explain is, so I mean, first of all, to finish explaining the main theoretical results of Watanabe in Bayesian statistics, and then explain how those results can be applied in well, for machine learning models at the end of the day. So a quick reminder, because I know that there was quite a lot going on. So the key result, or at least the key slogan, is this claim that the asymptotic Bayesian generalization performance of real analytic parametric statistical model in this context of IID data is controlled by singularity theory, so by the real log-canonical threshold of this relative entropy function between the data generating distribution and the model. So we've already seen a number of these. I mean, we've seen what these kind of parametric statistical models are, and I've discussed this real log-canonical threshold quite a bit. I've introduced this relative entropy. We still don't know what the Bayesian generalization performance is, and this is because before I stopped, basically just before introducing the Bayesian parts of Bayesian statistics, which has to do with priors and posteriors. But so let me just to remind you what we saw yesterday. So this real log-canonical threshold is attached to a real analytic function, and it measures it measures the analytic behavior of f around its zero locus. So there are these two invariants. So I mean, the main one is this real log-canonical threshold, which is a rational number, and then there is some secondary invariant, which is a multiplicity, which is an integer, and it controls this among other things. It controls this volume scaling of sublevel sets of f, the poles of the associated zeta function, and this Laplace, the asymptotic behavior of this Laplace integral. And this is the relevant thing for singularity for the statistics. And so there is a local counterpart, and the global quantity is really the minimum of the local ones. And this asymptotic behavior concentrates around the most degenerate singularity. So I didn't provide references yesterday, so I tried to collect some. So for real log-canonical thresholds, there is, I mostly mentioned this book of Arnold Hussein, Zadi, and Barsheko, but I also remembered that there is this older paper of Atiyah, which is quite important. I mean, which proved basically this meromorphic continuation of the zeta function, and so it goes quite a bit in the direction. And then there's this paper of Moriko Saito on real log-canonical threshold, which is one of the very few sort of papers which look into this. So for singularity theory itself, so sorry for the wall of references, but the most important things are maybe these first two, which are the two textbooks or the two books that Watanabe wrote on the topic. And there is, I mean, maybe more accessible, there is this recent survey, so this recent advances in algebraic geometry and Bayesian statistics, which is a very nice sort of survey of the theory from, I think, last year. Okay, and yeah, there are a few other nice references. And this is the developmental interpretability. So these are the applications in machine learning, and I'm mostly going to talk about these two, and there will be basically one slide about this. Okay, so then let's go back to statistics. So I remind you again. So yeah, there is a lot of notation. I mean, there's not that much going on mathematically somehow at this point. We're just moving things around, and but there is a lot of notation. And so the model somehow consists of, I mean, there's a data set, and this data set we assume for the sort of theoretical analysis that it's sampled from an unknown data generating distribution, Q of x. And we want to approximate this data generating distribution by the elements of a statistical model. So parametric families of probability distribution. So on X, on the axis, but parametrized by W. And phi of W is the prior distribution. So it's our sort of belief on the accuracy of various members of the model, and sort of a priori belief. And then we have all these derived quantities, and I've already introduced a few of them. So actually, let me, yeah. So this is just the same setup, and maybe I just remind you from this slide that there's this key assumption that, I mean, to use real analytic geometry and singularity theory, we assume that this distribution is real analytic. That's and so yeah, there's this relative entropy, and I put the definition again because it's really one of the main quantities, and so it was thinking a bit about it. So yeah, it's a way to measure the, you want to say the distance, but it's not a distance. So the difference between two probability distribution on the same space, and so it's this defined by this formula, which is reminiscent of the definition of entropy in information theory, and indeed it's sort of part of information theory. And there is so as a corollary of convexity of Jensen's inequality, you get that it's a non-negative, and it's actually at least it detects. I mean, it's not a distance, but at least it detects when 2 points are, two probability distributions are the same. And we apply this in particular to the relative entropy between the and I should actually I realize I've not been consistent, so probably I should always say the relative entropy between the true distribution and the model, and always sort of just because it's not symmetric. So yeah, so this is the real analytic function of this little W hidden here that we're going to study. And indeed, yeah, if the integral is converges and nicely, then this is real. Yeah. So as I said, so yeah, the Bayesian parts start with the prior distribution. So now it's and this is a problem. I mean, it's kind of at the beginning it's hard to keep track on what lives where. But so this is a probability distribution on the space of parameter of the model. And from this prior distribution, we want to construct a posterior distribution, which sort of records the updates, the update that we're making after looking at the data. And this is where it's called the whole enterprise is called Bayesian, because this is where we use the Bayes rule. So this posterior distribution is equal to this the prior distribution times this, which is so this is the probability of the data set given the model. So this is called the likelihood, divided by the probability of the data according to like the whole model, not just this individual W that we are. And so the likelihood, the probability of the data given a fixed W is because the data is IID, because data is independent. It's the product of these things. And then we just, to get this, we integrate over the whole of that. So now we're going to give name to these quantities, and actually to a small variant. So, for the theoretical analysis, it's better to change a little bit. So we're going to define the normalized partition function, or normalized marginal likelihood. So it's essentially the integral that we had before, but I divide by the true distribution. So I'm looking at the ratio of the model and the true distribution, and I'm integrating. And we can rewrite this actually in terms of this function, this empirical. Sorry, this I didn't recall, but there's this sort of empirical version of the relative entropy between the true distribution and the model, and you can rewrite to just play with this. You get this. Just writing something as exponential over log. And so and then the normalized free energy is just minus log of this z bar. And so we can rewrite this. We can also rewrite the posterior distribution in terms of this as in this way. Again, it's just a little game. But here we see finally why this why Laplace type integrals. The connection between the first part of the story and this one is because Bayesian statistics is all about this type of integral, and more generally, like integrals. If you want to look at the measure of a set in W with respect to this distribution, you're just going to integrate this somewhere, or yeah. And so this is why these Laplace type integrals are important. And the fact that, so in the previous discussion, just to simplify, I didn't put somehow a factor in front of it, but in fact, this factor doesn't change the asymptotic as long as it's positive. And if it's, even if it's vanishes along, you can still say something. But to simplify things, I'm always going to assume, whenever I have a factor here, I'm always going to assume that on W0 it's positive. Just, and then it doesn't change anything to the asymptotic behavior. Okay, so this is Fn bar. So this Fn bar has kind of a statistical interpretation. It's a bit subtle, but maybe I'll just read this part, and this is just in words what's written here. So this Fn bar measures, in some sense, how much the distribution of the data predicted by averaging over the model according to the it differs from the true distribution. So it is a kind of measure. It is a kind of measure of how well the model is doing. It's a bit subtle, but and it can be written in terms of a relative entropy. But it's a relative entropy on the set Xn, not X. Okay, so then what do we do with the posterior distribution? Well, we want to make predictions. We want to at the end of the day, we want to do something with this model, and so we define the predictive distribution, and the predictive distribution is just it's the average of the model according to the posterior distribution. So what this means is that now that I have my posterior distribution, I have some distribution of beliefs about how good the models is, and I'm just averaging over that distribution. And so you can also rewrite this way, and in some sense, what this means is that we believe that if we see a new data point, it will come up with this property. That's one way to say what we think we've learned at this point. So how accurate is this procedure? And this is where we get to the generalization error, because the Bayesian generalization error, so it's the relative entropy between the model and the predictive distribution. And so this makes sense. Now, this predictive distribution is basically our best guess for what Q is. And so, we measure the difference with Q with a relative entropy. So as I just said, the free energy, or this normalized free energy, and the Bayesian generalization, they're both sort of measures of the quality of the model. They measure slightly different thing, and they're connected by this thing, basically. So basically, this Pn is kind of a discrete derivative of Fn bar. And so a theme which is very important in Bayesian statistics and statistics more generally, but and that Watanabe is very concerned with, because it's sort of a classical topics in statistics is what's called model selection. So comparing two different models on the same data, and these two things can be used for this. I mean, the theme of model selection is interesting, but I don't have too much time to go into it. So it will pop up at places. But okay, so now again I put all of this, so now we've introduced all of these quantities, and somehow we've gone from a statistical model to some prediction and some measures of the quality of those predictions. And what we want to understand is basically what those measures of the quality of the prediction, how they improve when n goes to infinity. And so this is what's called statistical learning theory. This general theme of understanding how well statistical models learn. It's called statistical learning theory. It's not pretty self-explanatory name. Statistical learning theory. So I'm just going to explain a bit more precisely what it is about. So there will be a kind of general phenomenon which is of posterior concentration, which is kind of a first order effect, and And singular learning theory, or more general, is about somehow the next order term. And so this next order term, I'm first going to discuss in the case of regular model, where this is a very classical topics in Bayesian statistics. And then I'm going to explain finally Watanabe's main result. So yeah, so heuristically, I mean, just if our model is learning anything at all, we expect that as the number of data samples goes to infinity, first of all, the model will predict better and better, and so will generalize better and better to new data points. And so that means that the Bayesian generalization error will decrease, and the model will also become more confident in the sense that the posterior distribution will concentrate around the set of this set W0 of true parameters. So recall that we are in the realizable case. So inside of our model, we have this W0 where I mean so the true distribution is there, but the model doesn't. I mean, we don't know that, the model doesn't know that, and somehow but the more data we see, the more confidence we are that that these true models are actually true. And so this concentration will then imply something about the asymptotic behavior of this this normalized partition function and normalized free energy, and the two are connected by this equation that I mentioned. And the goal, I mean, probably should be one goal. I mean, there's actually a lot of, I mean, there's a lot more to statistical learning. Yeah, so there should be one goal, sorry, of statistical learning theories to quantify this. And indeed, Watanabe, in this context of singular learning theory, proves a lot of other asymptotic results for other interesting quantities. But I'm not going to go into it. I'm just going to concentrate on this. Okay, so this is sort of the. This is the first order term. It's just about the concentration onto W0, and so this is not due to Watanabe. It's I don't know exactly. It's quite a classical connection between Bayesian statistics and information theory, and it basically tells you why. I mean, it already shows that this function k, which we have somehow at this point maybe is completely unmotivated. That it has a fundamental statistical meaning. It tells you exactly how the posterior. I mean, it tells you the first order of the concentration of the posterior distribution. So namely, so the posterior distribution concentrates more exponentially quickly in n, and with a rate function which is this relative entropy k of w. And so I'm going to state it slightly imprecisely. It's a little. But the rough idea is that for any measurable subset of W, so just saying some open ball, it's already very interesting. Yeah. Which and basically think of this open ball as being either away from W0 or containing some point in W0. These are sort of the two cases. So this one is very rough because this is really this first order thing. So. This is telling us that the integral over that u, so the measure that the posterior distribution is giving to that u, is if the minimum of k is strictly positive, so if u is somehow away from W0, and again think just of a ball outside of W0, then this minimum is strictly positive, and then we have exponential decrease. If u contains some points in W0, then this minimum is 0, and somehow this actually nonsense. I mean, it tells you, it tells you that you don't have exponential decay. You have, and then somehow the challenge will be the next order. And somehow you can slightly, and more precisely, you can just take the log and just say that this minus log of this will always tend to the minimum. And again, this is slightly inaccurate. And so the question, so this is a very general thing. It doesn't, it's certain. I mean, it doesn't require to work with analytic model. It has nothing to do with analytic geometry. And so the question is, the question which is there is, can we refine the asymptotic when we are around W? And this is, so then this is the regular case. So yeah, so again, and this also doesn't require analytics somehow. As I define it, regular is basically saying that there is this unique minimum, which is a non-degenerate minimum, and it also works. Sorry? Yeah. No, they're right, actually, because of most. Yeah. So okay. It doesn't require a priori, it doesn't require analytics, but in fact, it's always hidden there. Yeah, so if you assume that the model is regular, and we assume, so remember I said that this phi should be positive. What does this condition mean? This condition means that a priori we thought that there was some chance that W0 was the right model. If we don't, I mean, for instance, if the prior is completely concentrated away from W0, of course the posterior is never going to concentrate around W0 because it's always going to stay on the support of the prior distribution. Okay, so we make this assumption. That's kind of necessary. Okay, then we have asymptotic behavior both for the free energy formula and for the Bayesian generalization. So yeah, this free energy formula. So it's so this EQ again is the expectation according to the true distribution. So the expectation of this normalized free energy is goes to d over 2 log n minus log c plus little o of 1, and this c is this constant. So I mean, the only thing that to notice, maybe, I mean, it looks like the constant in the Laplace approximation. That's not a coincidence, and it has this determinant of the Hessian. And then you have the asymptotic Bayesian generalization, which is this d over 2n plus little o of 1. So in the regular case, there is a famous result which somehow goes beyond that, which really tells you about the concentration of the posterior distribution itself. It's quite technical, but so I'm just going to try to. Yeah, the rough idea is that the posterior distribution becomes a Gaussian. I mean, after rescaling. I mean, so it's like it doesn't. It's usually sorry. We know that at the end of the day, it's going to concentrate on W0. So in some sense, it's going to become a derived distribution at W0 at the limit. But along the way, it's going to look more. If you rescale it, it's going to look more and more like a Gaussian distribution, and not any Gaussian distribution. A Gaussian distribution whose covariance matrix depends on the inverse of the Hessian. Okay, and maybe I omit this sort of maximum. Like, I mean, the question is where the Hessian is centered. Okay, and now we come to Watanabe's theorem. So this main result of singular learning theory, at least in one form. So now we assume that our model is a realizable real analytic model, and that the prior again has to be positive. I mean, you can again do something slightly better, but that's not. We write lambda for the real log-canonical threshold and m for the real log-canonical multiplicity. Then the posterior distribution concentrates around this most degenerate point, and so we have analogs of this free energy formula and this Bayesian generalization formula. So, but now instead of before we had d over 2 log n in the regular case, now we have lambda log n, and we have a log n term which is controlled by the multiplicity. And for the Bayesian generalization, we have lambda n or lambda over n, or instead of 2d over 2n. So yeah, so I mean the proof of Watanabe gives you a lot more, but I mean a lot more precise information. But the problem is that the precise information is more difficult to describe. So in particular, I mean like this constant c that we had before. I mean it's already kind of complicated in the regular case, right? In this singular case, it's I don't know that anyone has done anything with the formula. It's pretty, and also I mean this is very interesting, but I think it's still very complicated. Like the asymptotic shape of this posterior distribution. So it's not a normal anymore. It's more complicated to state. And in fact, this asymptotic shape is actually a distribution, not a distribution in the sense of Schwartz, not a distribution. And also, I mean, the formulas depend on the choice of a resolution, whereas these formulas don't. So that's somehow the thing that you can extract, that Watanabe extracts from this proof, which you can state without independently of the resolution. Okay, so I give a kind of sketch of proof. But yeah, it's really sketchy. So you fix a log resolution, and then the idea. So I told you the idea. At some point I told you that the idea is to control the fluctuation of the empirical relative entropy function around the true entropy function. Because somehow we have this Laplace integral, or this asymptotic behavior for k, but the posterior distribution involves kn. So you have to bridge the gap, and that's somehow the main new contribution beyond the sort of the asymptotics for classical Laplace integral, or this Arnold Gusen-Zadeh-Varchenko asymptotic. So you look at the difference, and I mean, by the central limit theorem, you expect for any fixed W that this will converge to a Gaussian. But there are some, I mean, a major problem with this, right? Here I'm dividing by, a priori I'm dividing by 0 if I'm on W0. And so this is kind of fixed by the resolution in the sense that you define, first you show that this actually makes sense on the resolution, so it's well defined. And when n goes to infinity, it converges. So not only for any fixed W prime, it converges to a Gaussian, but the whole thing as a kind of random function converges to what's called a Gaussian process. There's a small technical lie there, but and so on the resolution on W tilde, you have a very clean expression relating kn and k with this. So, and you have this fluctuation, and you have some probabilistic control over this fluctuation. I mean, part of saying that what converges to a Gaussian process is somehow it tells you that it doesn't blow up. It's, I mean, you have some control over it. And then Watanabe takes this formula, plugs it into the proof. I mean, so this whole proof with zeta function, inverse Manin transform, density of state, and Laplace transform at the end. And yeah, then there's a lot of work to do but then at the end he gets to this. So I'll discuss maybe some first sort of statistical consequences of this formula. So I mean, somehow then the rest of the talk will be mostly about the free energy formula. But let's look a bit at this generalization formula, because so this is the one that I've promised you. Basically, it's a precise formulation of the slogan of the talk. And so because of this, Watanabe calls this the lambda, so the RLCT of the relative entropy. He called it the learning coefficient. So sometimes also going to use that. So in the regular case, so lambda is d over 2, and so it sees the dimension of the model, or the parameter count of the model, and so we can kind of think of lambda as an effective parameter count, or half of an effective parameter count, or some kind of complexity measure. It's not clear how far one should take this intuition, but okay, it's maybe the first one to have. So lambda is always less or equal than d over 2, and so if you have some non-trivial singularities, it's probably going to be strictly less than d over 2. And so this means that singular models generalize better, in the sense that they have somehow, all things being equal. I mean, of course, this is an asymptotic formula, and but they generalize better to new data. So, and indeed, in the regular case, this formula tells you that regular models with more parameters generalize worse. And so this means that over-parametrization, so taking a model which is too large, which has too many parameters for the problem at hand, hurts generalization. And in some sense, this is the sort of classical statistical wisdom about over-parametrization. That if you over-parametrize, then basically what your model can overfit to the data, so it can interpolate very, very nicely between the data point, but outside of the data point, it might do something completely random and not generalized to new point. And this intuition is really based on the regular case. And somehow this is not necessarily true for singular models. And this is interesting because we know, and somehow in modern machine learning, that there are situations in which over-parameterized model can generalize very well, and so it's tempting to wonder if it's connected to this thing. And I think in some cases you can show that it's connected. Okay, so let's summarize. So So this the Bayesian posterior distribution of a model. So again, for now, I'm just concentrating on the serializable case. Always concentrates around the true parameters exponentially fast, and the rate function is given by the relative entropy. And then, so for a regular model, the posterior is asymptotically normal, and we have these two formulas. But then for general singular models, we have a generalization, and this is where the real log-canonical threshold comes in and gets its statistical significance. Okay, so that was the kind of the main theoretical reason, but there is quite a lot to do to get to applications. And let me try to explain why. I mean, first of all, I mean, certainly in the context of basic statistics, so there has been Watanabe and his collaborators and his students, yes, many students, have applied this and extended in many directions, and I'm not going to talk about most of them. So in particular, so I already mentioned that there are other asymptotic results in statistical learning theory, and in some sense, the other, I mean, the ones that I presented are the cleanest and the most theoretical, but there are other asymptotic results which are maybe more practically significant. So, for instance, this symptotic error of the maximal likelihood estimation, or asymptotic error, the cross-validation error, so which are more realistic techniques, let's say, than pure Bayesian inference. So there are these information criteria in Bayesian model selection. So again, the problem of comparing two different or two or family or whole family on the same data, and this will actually come back in a second, and many more. And so what I'm going to concentrate on a certain path towards applications really to machine learning and to very large models, which as I'm going to explain is it's difficult to do in a purely Bayesian way. I need a few more definitions. So, and this is part of going from theory to practice. It's really because in the theoretical analysis we sort of pretended that each of these symbols that I was introducing had the sort of the same, that I could just write them and manipulate them. But in practice, we don't know what Q of X is. It's the whole point. We don't have access to the data generating. And so in some sense, to evaluate, I mean, to do things more practical things, you have to sort of clean it from your formulas and introduce this unnormalized quantity, which only depends on the data the model in the past. So in particular, the analog of Kn and the more realistic one, the one that we can actually compute, is the negative log likelihood. So you can see that it only depends on the model and the data set, so we can just compute it. And the partition function, so it's like the previous one, but there's no normalizing factor of Qxi here. So I'm integrating this the likelihood function, and so this negative log likelihood that is and it's up to this one of n is minus the log of this. So I'm just integrating this against the prior, and so this can be written in terms of this way, and the energy is again the log. And I'm just going to reformulate the free energy formula using these quantities, and also making this small remark that Watanabe's approach gives you not. I mean, I'm putting in terms of the expectation of Fn, but you get there's a more precise result somehow in terms of the asymptotic behavior of the random variable. I mean, of Fn to the random variable of the data, and this is much more. I mean, this is closer to practice again, because we don't. I mean, we when we do statistics, we're not summing over all possible data sets. But the formula is very similar. But so now now we have I mean, because it's unnormalized, we pick up this first one, this n level 0. So that is any point on 0. It doesn't matter. I mean, this constant on W, and then the rest is the same. But this is actually, I mean, in this form of the formula, form of this formula is is more instructive because we see that this log n is kind of it's already a kind of, I mean, this lambda log n, this log-canonical threshold is kind of the secondary term. So somehow the dominant term in differential is going to be the I don't want to go too much into it, but it's kind of important. So the statistical interpretation, or one statistical interpretation of this formula is that if you are doing model selection by minimizing the free energy, and I haven't really maybe justified why you might want to do this, and this is where I take I sort of omitted it. But then if you minimize the free energy, that will be the trade-off between the model accuracy on the data, which is this. So I mean, this measures. I mean, if you're familiar with the machine learning terminology, this is kind of the training error. It measures how well your model is doing on your data. And on the other end, so maybe I should have put lambda log n. This lambda log n is the kind of measure of model complexity or degeneracy. And I mean, this trade-off in statistics between the accuracy of the model and the complexity is a very standard thing. I mean, people did it in the regular case a lot. But so this is saying that this becomes more interesting in the singular case because now lambda is this measure of coming from singularity. Okay. I just want to say a little bit about the unrealizable case, but not really, because it's, I mean, basically you try to do the simplest thing. I mean, saying that it's unrealizable means that k doesn't go to 0, so you just shift it to 0. And you try to see if it works. And the problem is it doesn't work in general. So, but this is really interesting. I mean, there are some statistical reasons why you expect that these asymptotic formulas do not hold. And what I mean by do not hold is that there are additional terms. For instance, in some situations, there are terms of order square root of n that are just there. And that, but so you need some additional assumptions. And so Watanabe shows in this book, in this second book, how to extend singular learning theory under this assumption called relatively finite variance. And it's a bit technical, so I'm not going to discuss it. And there's this very interesting paper which goes somehow a bit further and already explains some of these square root n terms. Yeah, and I think it's kind of an open direction in the subject. Okay, so now I want to do things in I want to do practical things. So I want to compute this quantity. So what can I compute? Well, let's look at the learning coefficient. So this log-canonical threshold of k. So Watanabe and again his collaborators and students have computed it in a number of cases, and I put simple in quotation marks because it is quite a lot of work to compute this thing, because it involves, and again, the sort of the only general method to do it is really resolution of singularity, or at least enough resolution of singularity that you can reduce to something like a toric situation, or I mean, well, yeah. I should have mentioned it, but in the toric case, there is kind of a combinatorial, like a polytope based formula for lambda. But so you have to do some work, and in particular, I mean, the most recent one is the case of this deep linear neural network. So this is linear network with a linear activation function, which seems very weird, and it's kind of only a model which is only of theoretical interest, but it's theoretically very interesting, and it's been studied a lot in machine learning. And so there is this paper of Miki Ayoagi that does this computation. It's really quite impressive. I mean, it's basically a explicit resolution of singularity of this. Okay, so but I mean, even if you could do it, there's this fundamental observation that lambda depends on Q. So in fact, when I say that compute here, in each case you have to take some information from Q to do this and to get a value of lambda. So for instance, in the case of deep linear network, so I mean the function that you're computing in deep linear network is just a matrix, so it's a product of all the matrices, and the quantity that controls lambda is the rank of this product. But you don't know that. I mean, yeah. So but from a theoretical point of view, it's actually a good thing, because it tells you that the same model generalizes differently from different distributions. So it means that singular learning theory is telling you something about the generalization behavior for different distributions, which is something that does happen in statistics. But from a practical perspective, it's a problem. Sorry? Oh no, so here it's because it's linear. So it's literally, I mean, here the activation function is like the identity function. So it's a really toy. I mean, from some perspectives, it's a really toy example. From some others, it's already pretty complicated. Yeah. No. I mean, for general neural network, nobody knows, and I mean, then it depends in some very complicated way in properties of Q, and we don't know how. Equi-oriented like no, and yeah, so I've been trying to understand a bit more the geometry of this result of Farrugia, and discussing with Richard. But okay, let's look at the other side of the formula. So the free energy and the free energy. So in Bayesian statistics, actually the free energy itself or the partition function is known to be very difficult to estimate. So okay, at this point it's a bit disappointing. We have this formula, and it seems to relate two quantities of essentially theoretical interest that we cannot. And I'm going to explain you to tell you how to save the day, or rather how Watanabe saves the day. Okay, so I mean this is unfortunate because I mean we know the posterior distribution. I mean it's here. These are all quantities that a priori we know, but up to this thing. And this is some integral over the whole of the model, and this is difficult. However, there is some very nice observation, which is that there is this class of algorithm, which I'm not going to describe at all. So this Markov chain Monte Carlo integration or sampling algorithm, and what they can do in particular is to construct approximate samples from a probability distribution, which is only known up to a constant, like this one. And so this means that we can sample, I mean, within sort of reasonable computational power limitation, we can sample from the posterior distribution. And so this the MCMC is really the sort of the way that people do a lot of this sort of practical applied Bayesian statistics. I mean MCMC and many variants and so yeah, this MCMC does not scale up very well to very large statistical model, and so in particular to large neural networks that are used in machine learning these days. And so you need to compromise and to make some approximation. And there's something in particular, what is used in the papers that I'm going to mention at the very end is this stochastic gradient Langevin dynamics. A sampler which is less accurate than this, but which is much less computationally demanding. Okay, but so now we have samples from this posterior distribution. Can we use this to get an estimator of the free energy? And so Watanabe says yes. And so this is this paper, this WBIC paper. And so WBIC means widely applicable Bayesian information criterion. And so the name is a bit mysterious. I mean, this Bayesian information criterion is sort of the information criterion is kind of a standard terminology in model selection. It's widely applicable because you can apply it without knowing the learning coefficient. Okay, so how does it work? It's a bit complicated, but it's sort of a variant of ingredients that we've seen before. I mean, we're going to average this function, but so we're going to do an expectation with respect to what's called the tempered Bayesian posterior, the inverse temperature beta. Okay. So what does it mean? This is a small variant of Bayesian inference, or Bayesian. Well, basically we introduce this temperature, and this controls so how much we update from data. And okay, I always mess it up, but okay. So for large beta, which means a low temperature, we're not updating. These are smaller than 1, right? So this is going to be, if beta is very large, it's going to be crushed, and so we're not going to update. Whereas if beta is very small, so it means high temperature. I mean, there's somehow an analogy with thermodynamics and statistical mechanics. I know very well and talk about. But, yeah, at the small beta, we are doing very large updates. The case of Bayesian, the classical Bayesian scale is beta is equal to 4. And so what Watanabe tells you is you should to estimate the free energy, as we'll see in a second, you should do this tempered. You should take the expectation of this, which we know, which is good for any given W, with respect to this tempered Bayesian posterior for this temperature 1 over log. So, and NCMC and DLD and I mean, the sampling method, they work just as well for the tempered Bayesian distribution. And so this quantity is much more computationally tractable than the free energy. And so here is Watanabe's theorem about this in this WBSC paper. So again, on some technical assumption, I mean, basically the same technical assumption as for the free energy formula. And now we have this setup of relatively finite variance. So it works in the unrealizable, in some unrealizable cases. So the free energy is this WBSC of n plus something of order square root of log n. And then if you combine this with the free energy formula, you get that WBIC itself is, so you have this NLN W0 plus n log n plus. I made a small, yeah, it shouldn't. We don't know what W0 is. So here you should actually put some maximal, like you should put maximal likelihood estimate, because you don't know what W0 is, but you can compute somehow the minimum of ln. So you just do that. And so what you do is you just take this formula and reverse it, and you define lambda hat to be WBSC minus this over log n, and again at the maximum likelihood. So it's an estimator of the learning coefficient. And so now this means that we can estimate the real log-canonical threshold of k from data. That's really the quite magical thing. Because it's square root of log n, you cannot actually get the log n term. So I have no idea actually how to get an estimator for the multiplicity. Okay. Yeah. So then, I'm going to talk about something that it's not maybe standard, but I would call local Bayesian statistics. And the problem is the following. So we even this, I mean, this WBIC is great, and this makes this singular learning theory tractable for reasonably sized Bayesian models. But we cannot. This really doesn't work directly on a large model. So I mean, and large being like millions or billions of parameters. Right? For the moment, it's only been applied to millions of parameters. Let's say millions of parameters. This is completely intractable, and it's also, I mean, and so in general, Bayesian statistics is really unprepared to deal with this kind of model, because Bayesian statistics is about integrating over the whole space, and you don't want to integrate over 1 million dimensional space. It's madness. And also, it's not clear that we want to do this, because actually in machine learning, what people do, because they can't do this Bayesian procedure, or they use optimization algorithms such as stochastic gradient descent, and I'm going to say a little bit maybe about it. And this explores, I mean, this is an optimization thing, and it explores a very, very small part. It basically explores a path through the parameter space. And so it completely, it doesn't care about what it doesn't see. So, and we want to understand this training process, because that's what is done in practice. And so the solution, and this is what that I would say Dan Murfet and his collaborators have figured out, is you should apply this. I mean, there are some also already in Watanabe, there are some remarks to this effect, so they really put it in practice. You should apply singular learning theory to the model that's obtained by localizing the large model to small parts of the parameter space. Okay, and there is this, this story of phase transition in the Bayesian posterior, which sort of comes with this, that I don't really explain. Sorry?
How do you take small parts?
Yeah. No, rather you, well, one thing you can do is restrict to a ball, for instance, like multiply by the prior. I mean, what you do is you change the prior actually. But since you want to stay in the analytic setting, what you have to do is this, and this is this local. So this is local learning coefficient estimator. So in this paper of Lau, Murfet, and Wei. Okay, this is quite a bit to take in, but it's really a synthesis of this WBIC idea and this idea that you should localize. And you localize actually, so not by, because you want, okay, let's say because you want to stay in the real analytic setting, you localize not by multiplying by some of the, by just, yeah, how do you call it? The indicating function, No, here you are going to multiply by a Gaussian, actually. Yeah, it's about. I mean, it's not a, it's a, yeah, so what you do is you have, so you fix a point, and this is the point around which you're going to do your estimation. You fix a confinement length, again, an inverse temperature, and this is just because, again, you're going to do the WBIC trick. And you define this local tempered posterior to be, so it is just the usual, again, tempered posterior, but multiplied by this confining Gaussian prior. So you're ensuring basically that, but you're declaring that you only believe in the models close to W, and you think that the models very far away have no, it decays exponentially quickly. And so then you do this WBIC procedure, but for this tempered local posterior. And again, you have to take a kind of local maximal likelihood estimator, so a local minimum of this function in the ball. I mean, here you kind of have some flexibility, but just for consistency, you take the same length. Okay. So do you have maybe it's time to pause for questions, because, and somehow this is the most complicated formula that we have, but I kind of had to go through it. I mean, this that useful has been already applied in application. And I mean, I'm not saying that it's the only thing that you can get out of this theory. In fact, I really hope that more geometric ideas and more can extract other interesting quantities. But this is the first one that really works does interesting things. Again, it's for this sort of local setup. Okay, sorry. So this is I didn't have time to make this shorter. So yeah, so this is about the relationship between this local learning coefficient estimation and the local RLC. So, and first of all, yeah, this confinement Gaussian prior, it ensures that as I said, the local posterior is concentrated around W, and so it's actually quite it's a bit sensitive to I mean, like if you sorry, I should have been clear, right? How do you compute this? Again, you use a sample. Yeah, I'm going to. And the sampler has some kind of numerical stability or instability, and you have to tune this. Okay, but this is really the key point. So sampling from this local tempered posterior is much easier than sampling from the full posterior distribution, because now we're still sampling from a one-dimensional space, but we're sampling for a very small ball in a one-dimensional space instead of the whole thing. And this is much more tractable, and at least empirically it seems to work. I will show you some results that suggest that it works. Okay, but so what is this quantity computing actually? See, this is also this is kind of interesting. So when the point is in W0, or we can sort of also expect when it's close to W0, then this WBIC theorem implies that this lambda hat is an estimator of the local real log-canonical threshold. So now we can compute local real canonical threshold from data. There is a certain idea, which is that, I mean, if you like if you apply it literally, the confinement prior actually is, I mean, this maybe seems innocuous, but it actually makes the model regular. Because you're adding, I mean, what it's doing to the function k is adding a quadratic form around w0. But the point is it's and this is where you have to, well, yeah, there's no really proof that that it works well, but somehow this thing that you add is flat enough that for reasonable size n, what you see is really the behavior of the singular the singular function, and it seems I mean it works. So you're not seeing the regular thing which of this. And I mean, and this is maybe a general remark that this is related to something that was mentioned yesterday. That so we have these theoretical quantities, and basically, what I mean, this real or canonical threshold is kind of, it's a semi-continuous rational number. I mean, when you apply to any problem with some finite precision, you're never going to be at the point. So you are making some kind of and okay, I have a I have a slide that in the end I removed it. Yeah, okay, so again, making some and this is not something that at least that you get a completely rigorous proof of, but making some reasonable assumption, you get an estimator of the local real log-canonical threshold. And the mystery, though, is that these quantities, this lambda, behaves well away from W0 for basically for other points in the parameter space, including points which are very far from the 2D solution. And it seems to give some kind of local complexity measure everywhere. And so it's not clear what this is measuring geometrically. Again, so some ideas, but okay. Also, so it works. And so this is why we can use these results of Ayoagi on deep linear network, because there we know the true value. And so in this recent paper, so Zach Furman and Lao, they compared. I mean, they compared this. And we know everything in this case. Well, we know at least enough to check the. They compared the value of lambda for points close to W0 and with the theoretical baseline of Ayoagi, and for models which goes up to 100 million parameters, and it's works very well. Okay, so now in the last 2 minutes, I'll talk about applications to machine learning. And this is okay. So I've already mentioned this many times, so maybe I go. So this notion of maximal likelihood estimation. So okay, let's forget about k. Let's just focus on ln. So minimizing ln is maximizing the likelihood, and what's called in statistics and machine learning maximal likelihood estimation. So for regression model, this is actually, I mean, this thing is basically the mean square error for the type of regression model that I discussed yesterday. It's really minimizing the mean square error loss function. And so how is it done in machine learning? Where it's minimizing this loss function is done by, I mean, it's an optimization problem, and it's done by some optimization algorithm. And yeah, so because these models are so big, you don't want, for instance, to do second order optimization. You don't want concomitant deviation because deviation is too big. It doesn't fit in your memory, and it takes a long time. So you just want to do first order. You just want to compute gradient, and you don't even want to compute the full gradient of the function because the function has a lot of terms depending on the data set. The data set is big. So what you want to do is stochastic gradient descent, and this is a sort of noisy, discretized version of the gradient flow of ln. And it looks like this, right? If these are the level set of the function. And basically what you do is you compute the gradient of somehow a sum of the, I mean, this ln is a big sum because it's a sum over all the data points, and you compute the gradient of a kind of sub-sum, for some random set of points. So, and this is where the stochasticity comes from. And then you just update. No, you just okay, and so developmental interpretability in this, and this is also a terminology that it's proposed by Murfet and his collaborators. And the goal is to understand the development of computational structure during the training by stochastic gradient descent of neural networks by tracking the changes in the local geometry. And yeah, the tools, I mean, they've started to think about others, but the main tool that they've used so far is this local learning coefficient estimator lambda. And so there are these two papers. So there's this TMS paper, so toy models of superposition. And this is very, I mean, they really understand a lot, not just from this point of view of this lambda and lambda, but like from the posterior distribution. I mean, you can really understand a lot. And there is this from this TMS paper. So these are different types of critical points of the potential that in this case, you can sort of classify. And there's sorry, I mean, unfortunately you can't see, but so this axis is the learning coefficient, and this is the loss. And somehow the shape of this curve is kind of also predicted by singular learning theory. And this is a more realistic thing. This is for a language model. I mean, it's not a large language model by models. Standard is like 2 million parameters, but and this is the loss function, and this is this local learning coefficient. And yeah, they can interpret these phases as developments of new computational capacity in the model. Okay, so that's let me stop here. I mean, I mean, because it's kind of just a number, right? So it doesn't see that much, but it's because so it sees kind of changes in complexity of the model or the learn function, like, and so there is a story, but which I haven't had time to present, which at least in the Bayesian setting predicts somehow that when n as n goes to infinity, you have kind of like phase transition in the location of the posterior, and this is actually quite well empirically really well supported by this in this small paper. But this phase transition story is unfortunately for larger models, so like this one, it's not enough to explain everything, because for this larger model, the loss function is decreasing, and this so in particular this means that you're actually not going close to a critical point of the loss function, and so the role of singularity theory there is a bit less. Then so they're thinking about how that plays out. But,
Value function.
So I wrote a slide in this complement. The non-analytic model. But okay, the main message though is that I mean, so Watanabe developed this theory in the analytic context just because this was I mean the ingredients that he had were available in this case. I kind of expect. I mean, I expect that for reasonable piecewise analytic function, and so in particular for like sub-analytic function, it could be possible. I mean, for instance, these asymptotic of Laplace integrals, they also exist. There are some maybe one paper about this in the sub-analytic case. I mean, the main difference that you lose in this, for instance, this rectified linear unique, right, is that, for this sub-analytic function, is that this is even further from algebraic geometry. So, like, to actually compute this RLCT seems very difficult. But I think the theory should really work. And the thing is that the practical solution so far has been to ignore issue, but it seems to work well. So this is also why I expect that somehow the theory should work in the same way with if you do it carefully in the sub-analytic.
I think for industry, you have to do this.
Yeah, this is a common question.
But there's also like small application functions you can use, not just values.
Yeah.
Non-linear, but still smooth. But they're not very. I know that it's not very.
That's common. Yeah.